Welcome back. Let's continue with the part 2 of our chapter 3, which is of motion and force in NET series. Starting with the first topic of equations of motion, which were given by Galileo, right? So here are the three equations of motion given by Galileo. We have final velocity is equal to its initial velocity added into acceleration times time. Then we have S stands for displacement, which is equal to the initial velocity times time plus half acceleration times time squared. And then we have the squared of final velocity minus the squared of initial velocity, which is equal to 2 times acceleration times displacement. Now, a very important point over here is that these equations are only going to work if your acceleration is constant, right? So if you have a problem which you would not really face, but in a problem where the acceleration is changing, then these equations are not going to work or do you any good, right? So you have to make sure that if when you read a problem, if the acceleration is constant, then these equations will be fine. Furthermore, these equations work exactly in the same way if you, instead of having some acceleration, which would be, it could be in horizontal or vertical motion, but suppose if you were only having a vertical motion where your acceleration of gravity would always be there, so you can just replace A with G. So in these equations, wherever you have A, you could just replace that with G, which is acceleration due to gravity. Moving on to Newton's laws of motion, let's discuss these laws of motion which Newton gave us. These laws were written in Newton's book, which he wrote, which was the Principia of Mathematics, and all of Newton's work in physics was or is in this book, that is Principia of Mathematics. And it is actually amazing that you can still find this book and you can see, of course, the translated version of what Newton really did in his work. And you can also find these Newton's laws of motion in the language of Sir Isaac Newton himself in this book, right? Now, the Newton's laws of motion are only applicable to objects which are moving with speeds that are much smaller than the speed of light. So c is here the speed of light over here, right? So this is a limitation to Newton's laws of motion, and it might seem as a problem. If you go deeper into physics, this is obviously a problem, because that means then these laws are not really laws if they're not valid, or if they need some condition to be true, right? However, when do we really encounter speeds that are close to speed of light in our everyday life? We don't really do that. We don't really see those objects that are moving very fast in our daily life. So for most of our daily work and daily use, Newton's laws of motion are enough, right? And now let's discuss these laws. So we'll start with the first law of motion. So the first law essentially states that a body will stay in a fixed state unless it is acted upon by some force, which just means that every body is going to be in either a state of rest, right? Or if it's moving in some direction, or let's say it's moving in a straight line with constant speed, it will stay in that state unless you apply some force to change that state of the system. And so clearly this first law of Newton, it defines what force is, right? Now, note that there is some inability of your system to change its state, right? According to the first law. as we discussed. So this inability of your body to change its state from one specific state to another state, this thing is known as inertia. This inertia, this statement is also known as Galileo's law of inertia. Moving on, so to second law, it states that if you have this force that is being applied on a body, it will cause the object to change its velocity, right? Which just means that it is going to produce an acceleration, and this acceleration is going to be produced in the direction of your force that you just applied. So mathematically, it can be represented with this expression, which says that force is equal to mass of the object times the change in velocity per unit time, right? But we know that change in velocity per unit time is just acceleration, and hence this law becomes F is equal to m times a. Moving on to Newton's third law of motion, it states that if an object A is going to exert some force on, let's say, an object B, then what happens is that the object B will always exert an equal but in an opposite direction a force on your object A, right? And so this third law, it represents a symmetry in nature, which is that the forces occurs in pairs, right? Which just means that if I have one body, it cannot just exert a force on another body without experiencing a force itself. And in modern way of thinking about forces in physics, you can think of this in terms of what is called exchange particles, right? So to give you an example, consider that you have a sea where there are two boats in that sea, and we have one person in each boat, as you can see. Now imagine if this person were to throw a ball to this person in this boat, what would happen? Well, as soon as this person releases the ball to throw it away, it would cause a change in momentum of this person's boat, and so the boat might start moving in this direction. And what happens over here is that when this person catches this ball, which was coming to him with some velocity, what would happen is that when the person catches the ball, its momentum changes, and suppose that the boat starts moving in this direction. So what really happened over here? We saw that there was a force that was produced by this person on this person, and then by this person in the opposite direction on this person, right? And so how did that force mediated is a word that we use. It mediated because of the exchange of this ball. And this is how we talk in particle physics. We term that this ball is that exchange particle, right? So you know a very popular force in nature, which is electromagnetism. And in electromagnetism, this exchange particle for electromagnetic force is photon, which is the particle of light. So mathematically, the law can be represented as follows. So we have force from person B to A, or you can read it the other way around, is equal to negative force in the opposite way, right? So if you were to say that this is the force that was from person A to person B, then that would be equal to negative of the force from person B to person A, right? This is also known as action, while this is known as a reaction force. Now let's talk about something which is known as an inertial frame of reference. So you would have some frame of references, right? And you can pick one frame of reference and then do your entire physics in that frame, right? So you can pick an object and say that that object has a frame of reference, right? So, an inertial frame of reference is a one in which your system or a mass is at rest relative to other objects, or you can also say that it is moving with uniform relative velocity. So, the acceleration for such a frame is equal to 0. So, you can say that the law of inertia is true in an inertial frame of reference. Next, we have, of course, non-inertial frame of reference. And of course, there is the one which is not moving with a uniform relative velocity. And hence, the acceleration for such a frame is not going to be 0. Some fun facts are that your Earth, planet Earth, is almost an approximate inertial frame of reference, and that is simply because the Earth is moving with a very small negligible angular acceleration. Well, I should not say moving, but I should say rotating, right? So it's rotating with a very small angular acceleration. Moreover, suppose that if you were having an environment where there is zero force acting in that environment, that means that only an inertial observer can be in that environment, right? Moving on, let's talk about momentum, specifically linear momentum, which is only which will work for things that are moving and not rotating, right? So things that are translating from one point to another. So in very simple terms, linear momentum, which is represented with this vector p, it is the product of the mass of your object which is moving with some velocity v. So any object that is moving would carry some linear momentum, right? So any object that is translating specifically would carry linear momentum. So suppose that you have a block of mass m which is moving in this direction with some velocity v, then your linear momentum is a vector that would point exactly in the direction of your velocity, right? Of course, this vector can be either small or it can be large depending on the mass of the object when compared with the velocity, but it will always point in the direction of your velocity. Hence, linear momentum is dependent on these two variables, which one is mass and the other one is velocity. Next, we have something that is called impulse. And the vector impulse is simply defined as the change in linear momentum. So something that is causing a change in linear momentum is known as impulse. And an impulse of a force is defined as the product of that force that was applied to change the momentum times the time or the duration for which this force F was applied on the object. So dimensionally, impulse has the same units of linear momentum. Hence, impulse is just impulse of a body is just some change in momentum of that body. Moving on to what is called the law of conservation of momentum. It simply states that for a system that is isolated from any force or any surroundings, right, the sum of your initial momentums is equal to the sum of all your final momentus. So suppose that you have two bodies, m1 and m2, then the initial momentums for that can be written as m1 v initial 1 plus m2 v initial 2, and this whole thing is equal to m1 times v final 1 plus m2 times v final 2. So you'd have something, for example, as this diagram. Look at this one. You have two balls and they're moving initially with v1. This is ball for ball 1, and we have v2 initially for ball 2, and they happen to collide with each other, and then the velocities or the momentums of these ball changes. So we have v1f and v2f. So you can write this whole diagram down mathematically as this expression that we see over here. So this diagram takes us to the next topic, which is of collisions. So collision may happen due to an interaction taking place between two bodies because of their closeness, right? So the closer they are, so you can think, you can look at this example and you can, well, you can immediately understand the whole concept of collision. Now collisions may be distributed into a group of two. First, we have a type of collision which is known as elastic collision. And in that, the kinetic energy and the linear momentum of your system is conserved. So that type of a collision is known as elastic collision. Next, we have inelastic collision. And for an inelastic collision, only your linear momentum of the system is conserved, and so the kinetic energy is not conserved. Next, let's talk about friction or friction force. So friction is essentially when a resisting force is created between two bodies that are rough, right? And it resists the sliding of one of the body over another body. And that is known as friction. So you can look at this diagram where we have two bodies, a black one and a green one, and these two bodies are sliding over each other, where black is moving in the right direction while the green one is moving in the left direction. This produces a friction force in this region, right? So here there is some friction force where some heating and all will happen, right, due to friction force. So the friction force is always going to act in the opposite direction to the motion of the object. So again, if you look at this example, the green body is moving to the left, and so the friction for the green body would be in this direction, right here. And for the black body, it is moving to the right, so the friction due to this one is going to be in this direction, to the left. Important point here is that this friction is independent of the area of the contact of two surfaces. So if you look at this diagram again, it is independent of this area of contact of these black and green bodies. So it doesn't matter if this area increases or it decreases, the frictional force will stay the same. So mathematically, we can define a term that is known as the coefficient of friction, and it is represented with the symbol mu, and it is the ratio of the friction force to the normal or the reaction force, right? F is also known as limiting friction, right? And so if you look at this object, there is some force that is causing this green object to move to the right, which is going to produce some limiting friction in the left direction, as you can see over here. And because of this object's contact with the ground, there will be some normal or a reaction force according to Newton's third law. And this ratio between the friction force and the reaction force is termed as the coefficient of friction. And this coefficient mainly depends on the nature of your material It depends on the surface of your material, for example, the finishing of this material, right? Or the film surface. It also depends on the temperature of the surface or the surroundings, right? We also have two types of frictions, and the first one let's discuss, which is static friction. And the static friction is going to play a role when there is a contact between two surfaces before the motion even begins to happen, right? And so you can write down the static friction as the static coefficient of your friction, right? So this is the coefficient of static friction times the normal force or the reaction force R. Next, we have kinetic friction, and this kinetic friction happens when one of the body is moving over another body. Then you have the friction is known as the kinetic friction, which is happening during the motion, right? And so you can write down the kinetic friction as the product of the coefficient of kinetic friction times the reaction force R. Now we can also define something that is called the angle of friction, which we'll represent with the symbol theta. So if you go back to this figure over here, this one, you can draw a resultant of your between your normal reaction and the friction limiting friction force. And the angle theta is the angle between your reaction force and the resultant R1 of your reaction and the friction force. Now, looking at this figure and recalling some of the laws of trigonometry, I can, from the figure that I just showed you, I can write down tangent theta is equal to the friction over the reaction force R, right? Which is just equal to the coefficient of friction, right? So with this, let's end this lecture part 2 for force and motion, and we'll continue in part 3, which would be the final part of this force and motion chapter, which would contain tensions and projectile motion.